Next chapter is lasers. Laser is an acronym for the instrument mode of action, which means light amplification by the stimulated emission of radiations. Laser light is coherent, which means all photons have the same wavelength and are in phase. Same wavelength and in phase. A laser beam is also collimated. It means the waves of light are parallel. The waves of light are parallel. Now the production of laser energy. Laser energy is produced by three stages: pumping, spontaneous emission, and stimulated emission. So first is pumping, first stage. So as you know that all atoms are stable in their lowest energy, known as the ground state. So this is in electron and it is stable in a ground state. Now when energy is given to this electron, here you can see energy is given. So energy is given by a process called pumping. This energy is given in a laser active medium. So this energy is absorbed and this elevates the electrons from their ground state to a higher energy level. From ground state to a high energy level. So electron go from the ground state to the higher energy level. So the upper laser energy level, the excited atoms accumulates there. So when there are more atoms in the excited state than the lower energy state, so this is known as population inversion. When there are more atoms in the excited state, population inversion is said to have occurred. Now atoms in this excited state, they are unstable and their electrons tend to spontaneously return to the ground state. And when they return to the ground state, they emit light energy. So they emit light energy. Now this spontaneous emission of light is incoherent and it travels in all directions, and atoms are less stable in their lower laser energy state. It can drop back to the ground state, and when they drop to the ground state, then they enter the new cycle. They go off, they go down again, and from this state they go back to the ground state. Our next stage is stimulated emission. Now as we told that the spontaneous emission of light is incoherent. So when an atom drops from the excited state. Now if an atom at the excited state is stimulated further by a photon whose wavelength is that which the excited electron would naturally emit. So if we give further energy by a photon which has the same wavelength which the electron would naturally emit, now the resulting emission will be coherent with the stimulated photon, and the electron will drop to a lower energy level. Now most of the energy which is released by spontaneous emission is incoherent, but the small amount which is released by stimulated emission, it is coherent, and this small amount can be amplified by a process called resonance. Now we will discuss resonance. Now the active laser medium is housed in a tube which has a mirror at each end. One of the mirror is made partially transparent to allow some of the light to leave the tube. Here you can see some of the light is leaving the tube. Now resistance between the two mirrors, this mirror and this partially transparent mirror, this distance between the two mirrors must be equal to a multiple of the wavelength of the light emitted, so that the resonance can occur. Now when inside this tube a stimulated emission occurs, which we have discussed, the stimulated emission. So the light which is emitted, it travels down the tube, and it is reflected and re-reflected at both mirrors, reflected and re-reflected. Then by that other stimulated emissions take place, and then the light travels down the tube. It becomes stronger and stronger while remaining exactly in pace, means coherent. So as one of the mirror is partially transparent, so some light it is allowed to leave the tube, and this light will be coherent. The wave fronts are in phase. It will be monochromatic. All light will be up one wavelength, and light will be collimated. All the rays will be parallel. Light is produced continuously, and such a laser is said to be operating in continuous wave mode, CW mode. That's why laser is an acronym for the instrument mode of action, means light amplification by the stimulated emission of radiation. So laser light will be coherent, monochromatic, collimated. Now the lasers are named according to their active medium. The laser active medium contains the atoms which will undergo stimulated emission. The laser active medium may be gas like argon, krypton, carbon dioxide. The laser active medium may be liquid like dye, and it may be solid like in NdYAG. The source of the energy which is pumped into the active medium. It may be electrical discharge, it may be a second laser, or incoherent light. Lasers are very inefficient in that a great deal of energy has to be pumped into them in order to maintain the lasering process. The lasing process. So, the actual luminous flux emitted by a laser is relatively small. However, because the luminous flux is not scattered in all directions but is concentrated in a fine parallel beam, so the beam of light is exceedingly bright. For example, a laser producing approximately 5 lumens of light may have a beam of luminous intensity 500 million candela, and a watt laser produces a retinal irradiance 100 million times greater than that of 100 watt incandescent bulb. Now, NdYAG means that the neodymium supported by a yttrium aluminum garnet crystal. Laser modes. The first is transverse mode. Comparison of cross section of the laser beam at different points along its path reveals that it is very slightly divergent and that it is more intense at certain points. So the laser light, it is generally regarded as coherent, but at a practical level all light waves are they are not precisely parallel, as they resonate between the two mirrors of the laser tube, and it is more intense at certain points and slightly divergent. The point along the path of the laser beam where it is least divergent is the point at which energy can be focused to the smallest part. This is called the fundamental mode. At the point of focus, energy is most concentrated at the center of the laser beam and diminishes peripherally in a distribution described by a Gaussian curve. Transfer modes are not so important when light energy is delivered diffusely, for example during retinal photocoagulation. However, for photodisruption like YAG capsulotomy, it is important to have precisely focused energy to achieve a greater disruptive effect. Newer YAG laser designs increase the distribution of energy towards the center of the beam to create a smaller point of focus and produce the same effect whilst delivering less energy. Non-fundamental modes representing divergent waves may be cancelled by an aperture inside the laser cavity to allow only a passage of parallel rays. CW or continuous wave mode. when a laser light is produced continuously. Such a laser is said to be operating in a continuous wave mode. And there is Q switching mode. As you know, the power is the energy per unit time. So watt is equal to joule per second. It means delivering the same amount of energy over a short time, it will have increased power. Lasers which are operating in mood locking or Q switch mode, they produce a brief pulse rather than a continuous wave of laser. The beam from a continuous wave laser like argon has a constant power output. Output is more conveniently measured in watts. The beam from a pulsed laser like Nd:YAG has a peak of power. Output is more conveniently measured in joules. Q switching is a mechanism whereby a shutter is placed in front of one of the two mirrors in the laser tube between which the oscillation of the beam normally occurs. Various shutters are used: rotating mirrors, dies, and electro-optic switches. This mode maximizes the energy state of the laser medium by limiting energy loss to spontaneous emission alone. So it limits the energy loss to spontaneous emission. So spontaneous emission is decreased. Opening the shutter allows oscillation to occur and produce a single pulse surge of stimulated emission with a duration of 2 to 30 nanoseconds. Mood locking. So in fact, laser light comparison mode comprises more than a single wavelength. It is not pure. So laser light is not pure. Various sub-wavelengths are not in phase, so-called free running mode. So some waves are not in phase. Waves alpha, beta and gamma. They have different wavelengths. They normally produce destructive interference. Now at time interval of T1, this is T1, they produce constructive interference. Here you can see constructive interference. And energy summation if they have already been synchronized at TO. So mood locking is refinement of Q switching, which synchronize the various wavelengths so that periodically they are in phase and summate here very high energy pulses. A pulse lasts about 30 picoseconds and produces up to 100 times as much as power per the same energy compared with Q switching. Effects of laser energy on tissues. Wavelengths from 400 to 1400 nanometer can enter the eye and reach the retina. The effect of laser energy on the ocular tissues depend on the wavelength, pulse duration of the laser light, duration of exposure, absorption characteristics of the tissue in question. So largely determined by the pigments contained within the tissue. The effect can be ionizing, thermal, photochemical. First one is ionization. Pulse duration which is less than or equal to a nanosecond may be sufficient to strip electrons from molecules to form a collection of ions and electrons called a plasma. So this collection of ions or electrons is called plasma. Plasma has a very high temperature and rapidly expands to cause a mechanical shock wave sufficient to displace tissue. So energy released as photons may produce a flash. The Nd:YAG and excimer laser work by ionization mechanism. Nd:YAG and excimer. Thermal effects. Light energy. So light energy is converted into heat energy if the wavelength coincides with the absorption spectrum of the tissue pigment on which it falls, and if the pulse duration is between a few microseconds. The important ocular pigments are melanin, xanthophyll, hemoglobin. Melanin is located in the RPE and choroid. It absorbs most of the visible spectrum. Xanthophyll, located at the macula, strongly absorbs blue light. Green is therefore safer. Hemoglobin, which absorbs blue, green and yellow wavelength. 10 to 20 degrees C rise in tissue temperature, photocoagulation and cause localized burns. Reaching up the tissue temperature to 100 degrees C will cause water vaporization and tissue disruption. The CO2 laser and the argon laser work by this thermal effect mechanism. Photochemical effect. So a pulse duration which is more than 10 seconds leads to formation of free radical ions, which are highly reactive and toxic to cells. Shorter wavelengths like blue ultraviolet cause damage at the lower levels of the eye radiance and are therefore more harmful. Argon laser for retinal photocoagulation incorporate a filter to protect the operator from the photochemical effects which might otherwise be caused by reflected light. Laser safety. The eye focuses on the beam on the retina, increasing the eye radiance, subsequently the risk by as much as 10%. International Safety Classification of Lasers. 1, 2, 3A class, 3B and 4 class. Output milliwatt in the safety. For blue green less than 0.024. For red also 0.024. For visible wavelength less than 1 is safe. For visible wavelengths 1 to 5 is safe. And for between 5 to 500 cause significant damage. More than 500 cause irreversible damage. All surgical lasers, including those used in ophthalmology, are classified as 3B or 4. They are capable of damaging the eye. So there are strict safety regulations which must be adhered. When there is a risk to the surgeon from reflected laser light, protection is provided by the shutters or filters built in the instrument, which operate when laser is fired. The filter absorbs the laser light but transmits enough light of the other wavelength to allow the effect of the laser on the target to be observed. The laser area should be free of personnel, but attendance of the other individual essential protective goggles should be used. Laser used in ophthalmology. Laser light can be delivered along a fiber optic cable to a slit lamp, indirect ophthalmoscope, and intraocular endolaser probe. First one is argon blue-green gaze laser. It is a mixture of 70% blue, which is 488 nm, and 30% green, which is 514 nanometer light. Commonly employed for retinal photocoagulation, to treat outer retina, spare the inner retina, to avoid damage to a nerve fiber layer. New generation are smaller, air-cooled, limit emission of green light. Argon green is well absorbed by melanin and hemoglobin. Xanthophyll in the inner layer of the macula absorb blue light but not green. Argon green, blue screened out, so photocoagulation of the macula does not cause direct retinal damage, while the use of blue light at the macula is contraindicated. Shattering of the laser light by a crystalline lens of older individual affects the focus of the beam and necessitates the use of much higher power setting. Helium neon laser, low power gas laser, visible red 632.8 nanometer emission, for aiming beam for laser with invisible output. So it is used in ND-YAG laser and diode laser. Diode laser emit wavelength of 810 infrared in continuous wave mode, are efficient, little excess heat, portable, absorbed only by melanin, so it is most commonly used for retinal photocoagulation. Low scattering of this wavelength, good penetration of the ocular media, edematous retina. 810 nanometer wavelength also penetrate the sclera. Even if the retina is obscured from view through the pupil, photocoagulation may still be performed by placing the delivering probe on the surface of the eye. Transparency of the sclera to a diode laser also allows photocycloablation of the ciliary body in the end stage glaucoma. Diode photocoagulation of vascular structures like neovascular membranes, tumors, enhanced by intravenous endocyanine, green dye with an absorption peak of 800 to 810 nanometer. Diode laser light has been used endoscopically to create decorous cystorhinostomy. Next is the erbium YAG laser. Deliver 2940 nanometer infrared radiation, absorbed by water, penetrates tissue by less than 1 micrometer. Absorption of energy by a very small volume of tissue results in the explosive evaporation of tissue, and thermal effects are limited to the surrounding 515 micrometer. This laser has been used experimentally to emulsify the lens in cataract surgery. Experimentally it is used. ND-YAG laser, which is most common, neodymium, yttrium, aluminium, garnet, emits 1064 nanometer infrared radiation. powerful continuous wave laser, usually Q switch when used to treat the eye, to disrupt the posterior capsule of the lens following cataract surgery or the iris in narrow-angle glaucoma. 1064 nm wavelength is invisible, so it requires helium neon laser red aiming beam. Before use on the patient eye, operator must ensure that the laser beam and the aiming beam are focused at the same point. Frequency double ND YAG laser emits 532 nm radiation. Its effects are similar to that of continuous wave or GAN laser. Excimer laser. The name is derived from excited dimer. Two atoms are gone in fluorine, forming a molecule in the excited state but which dissociate in the ground state. Emits 193 nm ultraviolet radiation. High absorption by ultraviolet by the cornea. Limits its penetration. Each photon is 6.4 eV, sufficient to break intramolecular bonds. Delivery of a relatively high level of energy to small volume of tissue cause tissue removal. Ablation. Ablation depth may be precisely determined. Although temperature and a tiny volume of treated tissue becomes very high, amount of heat produced is very small. No significant rise in temperature of adjacent tissues. It is suited for PRK, photorefractive keratectomy, LASIK, laser intrastromal keratomiliosis, PTK, phototherapeutic keratectomy to remove abnormal corneal soft tissue. Carbon dioxide laser emits 10600 10600 nanometer mid-infrared wavelength, strongly absorbed by water and by most tissues. 90% energy is absorbed within 200 micrometer of the surface to which it is applied. Only effects are thermal. The diffuse of heat from the target's coagulates adjacent tissues. The water vaporizes, releases steam. Such lasers are used in other branches of surgery to produce nearly bloodless incision but have yet to find use in ophthalmology. Holmium laser used to create sclerostomy to increase aqueous humor outflow in the treatment of glaucoma. Thermokeratoplasty to change the surface curvature of the cornea. ND-OILF laser, neodymium yttrium lithium fluoride, emit 1053 nm, picosecond 10⁻⁻12 pulse duration, which can be delivered at a very high repetition rate. Experimentally, it is used to dissect rather than disrupt tissue. Used to create sclerostomies, dissect vitreous membrane, change refractive errors by the intrastromal ablation of the cornea.